We're going to concentrate here on condensation polymerization. In the other video a couple of pages ago, we looked at addition polymerization, and just a quick recap of that. Addition polymerization was all about making plastic, and we started in addition polymerization with ethene molecules, an unsaturated alkene. The alkene comes from cracking long chain alkanes. Anyway, we take these alkenes, we take lots of them together, we heat them up. And this double bond breaks apart. The double bond breaks apart in every single one of these molecules, and we end up forming. Then end up all joined together. And we end up forming a hugely long hydrocarbon chain, and that's where all the monomers add together. Hence, it's called addition polymerization. Well, this one is different. This is called condensation polymerization, and condensation, I'm sure you associate with water. Water vapor from the atmosphere maybe condensing on a cold window pane, and we call that condensation. So the word condensation has links to water, and that's how this that's a big clue to how this type of polymerization works. Now, this type of polymerization is not between unsaturated compounds like alkenes. This type of polymerization is between two different homologous series. So before we can go into condensation polymerization, we have to know two new homologous series. And these homologous series are alcohols. Now, I think alcohols, what's unique about alcohols is the functional group. I will use the letter R just to indicate a carbon chain. So that could be 1, 2, 3, 4, 5 carbons, just letter R. But that carbon chain is joined to something completely unique. It is joined to an OH group. So that OH group is the alcohol group. So meth tells us 1 carbon, and the ending anol tells us it's an alcohol. So 1 carbon with that now functional group, OH, looks like that. And we now need to put hydrogens around the carbon to finish off the bond. So that's methanol. Our word for 2 carbons is F, and the ending anol, because it's an alcohol, anol. So now we need 2 carbons here. Decorate those with hydrogens. That first one at least, then we'll do the second one in a moment. Put the functional group on, OH, because it's an alcohol, and we're going to need a couple of extra hydrogens on that carbon now to finish off. That's ethanol. Propan-1-ol. Well, prop is 3 carbons. Now, the fact it says 1 there tells us the functional group, the OH, is on the first carbon. And now you may be looking at me drawing this, thinking to yourself that I've just drawn that on the 3rd carbon. Well, again, what you have to remember is these molecules don't stay still, they're moving around all the time. So if this molecule to move around like that, in other words, flip itself over, sort of turn itself around, if you like, then that OH will be on that carbon there, wouldn't it? So you can't have propan-3-ol because that doesn't exist because the molecule can turn around. You can only have propan-1-ol and propan-2-ol, because if that OH group were on the 2nd carbon there, that would be propan-2-ol. You only need to know propan-1-ol for GCSE. Likewise, butan-1-ol. But is 4 carbons. Okay. And we'll put hydrogen around everything else. You can have butan-1-ol and butan-2-ol. You can't have butan-3-ol because that would be butan-2-ol. It's just turn the molecule around. The same, you can't have butan-4-ol. That's butan-1-ol. So that's our alcohol group. The functional group for each of these is all identical because that's the same for all alcohols. So that's the first homologous series we need, alcohols. The next homologous series we need carboxylic acids. The functional group here, R, is a carbon chain, and we have a double bond to an oxygen and a single bond to oxygen and a single bond to hydrogen. So that's a bit like the alcohol group, isn't it? But it's not, because the carbon also has a double bond to an oxygen. Okay, the first one is called meth, because it's got 1 carbon, anoic acid. So this ending here, anoic acid, that tells us straight away it's a carboxylic acid. That's the functional group, and that's the unique ending to the name. So 1 carbon, oxygen, oxygen, hydrogen. Well, that's our 1 carbon, so that's our meth bit, so we just need a hydrogen attached to it. Methanoic acid. Next one, ethanoic acid. You know it is vinegar. Methanoic acid. Ethanoic acid, vinegar. Oxygen, oxygen, hydrogen, and now we need another carbon there, and put the hydrogens around it. There we go. Notice this carbon's got 4 bonds, it's got no hydrogens around it. 1, 2, 3, 4, so there's no hydrogens around that. Ethanoic acid. Next one, propanoic acid. Okay, 1, 2, 3 carbons. There's our functional group. Hydrogens around the rest. And I'm not going to do butanoic acid because I'm conscious of time. Functional group for all of these, all the same. Okay, now back to condensation polymerization. We've looked at these 2 homologous series. Okay, because for condensation polymerization, you need a molecule that has 2 alcohol functional groups on it, one on either end, so there'd be an OH on the other end and an OH on that end. That's and you need a molecule with 2 carboxylic acid functional groups, one on either end, one on this end and one on the other end. Let's go to the next page and hopefully you'll see what I mean. Okay, so here are our 2 molecules. Okay, this is our 2 carboxylic acids on this one, 2 times carboxylic acid functional group. On that one, C double bond O, OH, C double bond O, OH. That's the smallest possible molecule we can have for the carboxylic acid one. And here we have a molecule with 2 alcohol functional groups, just carbons with hydrogens surrounding it, but an O and an H. Now, the clue is in the name, how these join together. Condensation polymerization, okay? What we need to cut out of these 2 molecules is a water, okay? So, the oxygen and hydrogen on the carboxylic acid, okay, and the hydrogen on the alcohol, okay, get cut out. So they get lost. So that's over here on the water. So these 2 react together and water is cut out of the middle. Now the remaining bonds then join up. So that carbon there joins to that oxygen there. Okay? And so hopefully you can see that in the middle here. That carbon double bond oxygen is that carbon double bond oxygen there. That oxygen is that oxygen there. And that carbon 2 hydrogens is that carbon 2 hydrogens there. So that gets cut out with these 2 molecules, but what's happening at the other end of this molecule as well? This hydrogen is going to drop off here, okay, and join to another carboxylic acid group on another molecule. This oxygen hydrogen here is going to drop off that one there, and that will join to another alcohol group on another molecule over here, because there's going to be billions of these molecules in the beaker. And that's why we have the bonds going through the bracket, okay, because we can't draw out billions of these molecules, we have to stop somewhere, okay, and that's why we have that bond there going through the bracket there and the N outside. The N outside means lots, so really we should have N next to that molecule and N next to that molecule to say lots of those molecules as well. So what would a section of this polymer look like if we were showing 2 repeating units? Well, we'd just draw this twice in brackets. So we just simply need to copy that out, not once, but twice. Okay, so that is that part of that molecule there, joining to the oxygen, which we've already said is on the alcohol here. Then the alcohol molecule in its entirety. Okay, let's put the hydrogens around that. Okay, and that's that molecule finished. But that's 1 repeating unit. We now need 2 repeating units. We just need to draw exactly the same thing again. So carbon, double bond, oxygen, carbon, double bond, oxygen, carbon. There's a couple of CH2s. Oxygen, and through the brackets. That's now 2 repeating units. Brackets through it, N outside. Okay, so this is called a polyester. Okay, this is a whole nother functional group. The ester, sorry, no, functional group. Yeah, a whole extra functional group. I was going to say a whole extra homologous series. The ester homologous series. An ester is where you have this carbon double bonded to an oxygen, bonded to an oxygen. Okay, bonded to another carbon chain. So we've got a carbon chain here, bonded to double bond to an oxygen, oxygen, and then to another carbon chain. What is the ester functional group? So it's R for the carbon chain, carbon, double bonds to an oxygen, single bond to an oxygen, bonded to another carbon chain. And this is a polyester, so you have lots of esters joined together. So let's have a look at some other examples. We've got this one here. 3 carbons now with the 2 carboxylic acid groups and just the 1 carbon in the alcohol group. Remember what we said, we take the oxygen and the hydrogen from the carboxylic acid and the hydrogen from the alcohol, that's the water. So we just need to draw that, so join into that, 1 repeating unit. So I've got, so it's a repeating unit, so let's have a bracket going through that. So we're going to take the oxygen and hydrogen off this end as well. So let's have carbon straight away there, double bond to oxygen, carbon with a CH2 in the middle, carbon, oxygen, bond. Okay, so can we see all I've drawn there is this bit here, but without the oxygen hydrogen, because they get taken off to form water molecules. We're now going to come over here and I'm going to go straight to the oxygen. Oxygen, CH2. Okay, and that hydrogen is going to get taken off to form a water molecule as well. So oxygen through the bond now. Okay, N times. For 2 repeating units, I'm going to draw that not once, I'm going to draw it once, but twice, brackets around either side, exactly like we did with that one up there. I'll do one more and then you can do the next one on your own. Right, 1 repeating unit this time. This time I've got 1, 2, 3, 4, 5 carbons. Okay, the oxygen hydrogen comes off, the oxygen hydrogen comes off. Okay, so let's quickly draw that out, bond through the brackets. Carbon, double bond, oxygen, CH2, 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 carbon, double bond, oxygen. Okay, so I've drawn all that out now. Over here, take the hydrogen off that, straight into the oxygen, and the hydrogen off that end. 1, 2, 3, 4 carbons. Okay, so oxygen, carbon, CH2, 4 CH2s. Okay, so these are quite easy once you realise you've just got to cut water out and you take the oxygen and hydrogen from the carboxylic acid and just the hydrogen from the alcohol. Okay, so I forgot my oxygen there. There was no oxygen there, wasn't there? That's better. See how it's easy to make a mistake, isn't it? Carbon to oxygen, and then the bond goes through the brackets, N times outside. 2 repeating units, you have to do it a bit smaller on you because that's just 1 repeating unit. You need to do that once, twice. Okay, so now we've got down here problems about polymers. Now, I'm not going to write all these out now. What I am going to do is point you in the direction of the specification, the exam specification, because it's a great resource if you don't know what you've got to write. So if you're working from this book, here it was page 67 and 68, the exam specification for this topic 9, hydrocarbons, polymers and alcohols and carboxylic acids. Okay, if you're working from a different group, you can just get the specification quite easy off the internet. Okay, so it says here, down number 14, be able to write about some of the problems associated with polymers. These must include the availability of starting materials. Okay, so oil is a non-renewable resource. It will run out. It then says they do not rot. Plastics do not rot in landfill sites. They're non-biodegradable. That means they're just there forever and ever and ever. They do not rot in the landfill sites. Number 3, if you burn them, you can burn and incinerate waste, but that can produce toxic gases. That's obviously not great for the environment or people. When plastics are recycled, so we do want to recycle them, but there's so many different types of plastic, it's just a nightmare because they have to be sorted by hand, it's time consuming, it's very costly. Okay, so we've got the advantages and disadvantages of recycling polymers here, economic implications, availability of starting materials, and the environmental impact. So that's a great source of information, and you can use that source of information to fill that box in there on page 80, find it yourself. Okay, and the last one here, you need to know there's polymers in living things as well, and they're formed from following monomers. So glucose, sugar molecules form starch. Okay, nucleotides, they form deoxyribonucleic acid, in other words DNA, and amino acids form proteins. You need to know the monomer and the polymer that they form, and they form that through condensation polymerization, and that is condensation polymerization finished.